I'm Ben Lau,
Jacob.
and our project is low-cost underwater acoustic modem networks. Our graduate mentors were Chung Fan, Li Wei, and our faculty mentor was Dr. Jiabu Wang with the Department of Electrical Engineering and Computer Engineering at Michigan Tech University. So an abstract or an overview of our projects. In a communications network, there's three main components. You have the controller, a transmitter, and a receiver. For our underwater acoustic modem, a universal software radio peripheral device, model number X310, acts as our controller, a transducer acts as our transmitter, and a hydrophone acts as our receiver. By utilizing a software called GNU Radio, we're able to create a software-defined radio, or CR, system that does not need any hardware to simulate. This translates to the real world by connecting physical components to our computer and then executing the design flow chart. This project built upon previous senior design projects that attempted to prove a proof of concept by exploring ways to minimize costs as well as to make the system more efficient. A major breakthrough that we had was finding out that the off-the-shelf hardware that we were using for our system was not compatible due to the low voltages and high frequencies we were using. And so moving forward, we needed custom circuits may or may not need to be designed. Simple introduction. Acoustic waves are used when relaying information underwater because sound waves travel more efficiently than electromagnetic waves in that environment. Applications of this technology would allow sensors to remain fixed underwater and to transmit their data via acoustic waves to a central controller floating on the surface. And then if desired, it could then transmit that data via electromagnetic waves anywhere else it is needed. Currently, the cost of implementing such a network is pretty costly and very intensive. So our goal is to lower the cost by improving on existing technology, thereby making it more accessible to more people.
So exactly, we did this experimentation in the lab. And the experimental underwater setup in the lab uses two computers connected with an Ethernet cable to two separate USRP X310s. From the transmitting computer, the signal is sent through a USRP to an amplifier that raises the signal to the 1 to 10 volt range from an input of millivolts. And that goes out to the transducer, which then propagates the wave. And then the other USRP picks them up with the help of the hydrophone, and that gets sent into the other computer where it's decoded, demodulated, and recovered. The air experiments, the USRP amplifier and transducer and hydrophone were not needed. We just needed a speaker, a microphone, and of course two computers. The beauty of SDR or software-defined radio system is that once we had a successful code that worked in air, we just needed to change blocks in order to get it to work in the water system.
So on the middle of the screen, you'll see our experimental setup, and you'll see the flow chart. This particular screenshot was from, one moment. So this particular flow chart is from our over-the-air experiments. The message starts out with this little message box in the GUI. So on this computer, it will pop up and populate a little box where we can type our strings or our messages. From there, it goes to all these other blocks that act as the source encoder and the channel encoder. And our simulated channel is this audio sync right here. So this audio sync is in Jacob's computer, it's the speaker. And so that emits the sound that my computer will hear from this audio source on this other flow chart. This is actually the same program. It was just broken into two screenshots for consistency. And then on my computer end, it'll demodulate the signal through these various blocks. And then in the file sync, it'll actually save the file or save the data that it decoded from the file. And in many cases, we were sending a file that simply said hello world, or the strings, for example, right here we see 11001101, which would then appear in the file created on my computer. When we moved to an underwater setup in the lab, we had two computers, my computer and Jacob's computer, two USRPs, the power amplifier, the transducer and hydrophone are hanging in the water. They're not touching the bottom, so that way they're not any outside noise or any echoes. And once again, Jacob's computer will transmit the signal into the USRP, into the amplifier. Through the transducer, it will be picked up by the hydrophone, which will then send the signal to this USRP on the top, which is connected to my computer, which will then decode it. However, while we're conducting the experiment, we noticed the input signal from the transducer, or from the USRP, was in the millivolt range, and when it was going through the amplifier was not sensitive enough to pick up such small changes, so it didn't really amplify it to a usable degree, and the noise level was just way too high from the surrounding equipment compared to the signal level that we had.
So when transmitting a simulated message through the software, we were able to successfully recover the original message at a time. This was likely due to the fact that there was no outside noise in the channel environment, and the only factors were our blocks and the parameters that we set them to. When transmitting a message over the air, we were able to recover the original message and use just the frequency shift keys.
We were not able to recover the message when we attempted to use OFDM to transmit the message.
When we moved to the water testing, we were only able to recover messages sent via FSK using USRP and only
on attempt.
Again, this is likely due to the very low signal to noise ratio that was produced
by the amplifier. On occasion, we were
able to recover the original message from
the air.
This happened randomly and is consistent with random noise entering the system. When running our program through a closed-loop USRP system, we were able to recover our message because no noise could enter the system. We were able to recover the message once underwater because it sent
enough packets that by sheer luck, a couple of them were recovered.
So in conclusion, we have successfully demonstrated that while underwater acoustic networks are a viable option, there are many things that have to be perfect and even more things that could go wrong in order to get them to work. By using FSK to transmit the message, we were able to establish a proof of concept. And if we were to continue the research, we would further develop our OFDM program so that the system is now practical in the real world. OFDM would be preferred method to FSK because it allows for more information to be sent quickly, and as such is more bang for your buck. It's a greater investment since this is pretty costly, and so you would want the best system you can working. As an acknowledgement, we acknowledge support from the NSF Award number 2050739, and then mentorship and guidance from the QNL Bay Indian community, as well as our mentors, Chung Fan, Li Wei, and Dr. Jiahui Wang. And for reference, Dr. Wang happened to write a book in this very topic called OFDM for Underwater Acoustic Communications, which proved instrumental to our basic understanding, as well as our a little more in-depth and trying to establish experiments. Thank you.